Alright, this time we are going to compare the exponential growth with exponential decay. So these are two possible situations that you will encounter that when you are dealing with exponential functions. So exponential growth obviously is when you see that there is an increase in the value of the function. Decay is when there is a decrease in the value of the function. Say for example, the one that we have with Milik's car, wherein the formula that we obtained was, let's say C of t is equal to 15,000, which was the initial value of the car, then multiplied by 8,500, which is now the rate of the remaining value of the car, and that's raised to the power t. Okay, now for the population growth, let us consider one of the example there. Let's say P of t. That's P of t is the population of a certain place, maybe at a certain time t, and that's going to be 2,000. Let's say, what's that number again? We have 2,000. All right, 2,519. That's the initial population, and we multiply this number by 1.0177 t, because we know that the growth was about 1.77%. So therefore, the following year, the total the new population would be about 101.77% of the original population. All right, but this is now the decimal form of that percent. Okay, so we can see that the rate here, or say, let's take a look at the similarities. So similarities, basically, whether it's where there is a growth or a decay, we still have to mention, or we need the initial amount or initial value or initial population. Then we also have the rate. Okay, we have the rate for both, and then the rate is raised to the exponent t. All right, so here for the rate, our rate is, in this case, is 1.177, and the rate for this, in this case, is 0.85. All right, then for the value of t, if you're given the table or if you're given the graph, you will see that the values of p are increasing. Okay, and then for the decay, the value of the function, you will see that they will be decreasing. That's why it's called a decay. It drops, the value drops, the value depreciates, increasing, the value appreciates, there is growth, increase. So those are the key terms that you will see that will indicate that there is growth. All right, so our B here, remember that is just our rate, the amount that you constantly multiply to the initial amount. And what can you say about this? All right, one way of comparing these two is, if there is no change in the initial value, then therefore what you have, remember the initial value is 100%, right? If there's no change, then the remaining the following year, the value will still be the same as the original. Okay, but then if there is a growth, we can see that the rate is going to be what? Greater than 1, because it's going to be now greater than 100%. So the B, or the number that you constantly multiply here when it is a growth, is greater than 1. But if it is a decrease, you will see that the rate is less than 1. All right, so when you're given situations and you're asked to determine whether it will result to a decay or a growth, all you have to do is look at the rate. That is the amount that you are going to multiply to the initial amount. If it is greater than 1, then it's obviously going to be a growth. If it is going to be less than 1, it's going to be a decay. All right, so let's have an example. Let's say you have g of t here. That is, let's have an hypothetical. Initial amount is 50, and then we have the rate of 1.5t. So you see, I assigned a number that is greater than 1 so that we can have a growth. All right, so if, let's say, if we have g of 0, that means when t is 0, that means the starting time, that this will have 50. Why should it be 50? Because when t is 0, so that means the exponent here will be 0. So 1.5 to the power 0 is just 1. And 1 times 50 is just 50. All right, what if we have g of 1? So g of 1, so t is equal to 1. 1 month, 1 year, 1 day, after 1 hour. So depending on the unit of time. And that will be 1.5 raised to the power 1. And that will give us 75. Alright, so now you see from g of 0 to 50, g of 1 is now 75. So there is an increase. So if you increase your t, then the value of your function also will increase. Alright, now what about exponential decay? Let's have an example. Let's say you have h of t. Let's still use 50 as our initial amount. But this time our rate would be 7500ths. I mean, yeah, 7500ths, and that's raised to the power t. So when you have h of 0, which is the initial value, that will still be 50, right? But if we have h of 1, that is after 1 month, 1 year, 1 day, 1 hour, depending on the unit of time. So that's going to be our h of t. And what's the value of h of 1? So what's the value of h of 1? So that's 50 times 7500ths raised to the power 1. And that will give us about 37.5. Okay, whatever is the unit. Okay, so you see that there is a decrease of amount from 50 to 37.5. So as you increase the value of t, you will see that the value of the function here will also decrease. So that's why it's going to be a decay. All right, let's have an example. Okay, we have Kelly's mom who takes a 50 milligram dose of aspirin. So it says that each hour the amount of aspirin in a person's system decreases by 29%. Decreases by. So obviously, this is going to be a decay, right? And then, so how much aspirin is left in her system after 6 hours? By the way, this is only a hypothetical example. Okay, so these numbers here are hypothetical. All right, so what is this 400? So 400 is going to be our initial amount of aspirin, right? That is 400 milligrams. And then what is the rate at which this amount decreases? It is 29%. So if the amount of aspirin decreases by 29%, what percent of the aspirin original amount is left in the body? So how do we determine that? So we have to subtract 100 by 29, and that gives us 71%. So only 71% of the original amount of aspirin is left in the person's body after an hour. All right, so our rate here will not be 29%, but it's going to be 71%, because 29% is the rate of decrease. What we're looking is what percent of the original amount is present in the body, and this is what we need, the 71%, and that's going to be our B. If you want, okay, since we need to express that in decimal, that's going to be 7100ths. All right, so our initial amount is 400. All right, so what is our equation, or our equation? So we will say D of T, that is the dose or the amount of aspirin present in the body. So this is the amount of aspirin present in the body. after T hours. All right. Okay, so that's our indication, right? And of course, T here is the number of hours after taking the aspirin. All right. So what's going to be our D of T? Remember, we need what? The initial amount. Then we multiply that to the rate, and the rate is raised to the power T. Okay, so we have D of T. Initial amount is 400 milligrams multiplied by the rate, which is this 7100, not the 2900. Okay, because that's the rate of decrease. So what we need is the rate, the amount, okay, the percent or the amount of the original amount that is present in the body. All right, so that's going to be 7100s and raised to the power T. Okay, now, because we are asked how much aspirin is present in her body after 6 hours, so our T is equal to 6. So we are looking for D of 6, and that's equal to 400 times 71 raised to the power 6, and that's equal to, all right, so we need 400 times 7100 raised to the power 6, okay, and that gives us about 51.24 milligrams of aspirin. So that means after 6 hours, about 51 milligrams of aspirin is present in the body. So that's our interpretation.